that I believe all humans, all scientists would be interested in knowing the answer. I'll try to answer it with a concept called Murali concept. It's a radical perspective. And I'll talk about my background, all that in the times to come, within the next 1.5 hours. And I currently am stationed in a place called Shornu. It's in Kerala. I work out of my own trust. It's called Satyamjayatu. So, before I start my work, I have to pay my tribute to my mentor, Lowell Hager. He passed away in 2014. He was a wonderful man. He made me who I am today. And every time we parted, I visited him after I went out of Urbana-Champaign. I did my postdoc there. After I went out, I visited him thrice. And each time we parted, we hugged and we kissed. We were that close. I love him, and he'll live on in my works forever. Every manuscript that I've communicated after I became a corresponding author, it's dedicated to Lowell. I have acknowledged him. So, thank you, Lowell. You live in my memories forever. So let me come to the outlay of the talk. I'll be talking about the story of Murali concept, the paradigm that I'm proposing as an answer for the questions that I've set out to answer. What is wrong with the chemiosmosis theory of cellular respiration? This is what Andrew was expecting me to talk about first. That's the first thing that I'll talk in the crux of the talk. Before that, I'll give you an introduction. And then I would say how Murali concept, the paradigm that I'm proposing as an answer, how does it address those? And then I'll come to the projections. Now, before I start off my talk, I just want to take a stock of my, make a few clarifications and take a stock of my audience also. So, before I start off, I must say that criticism is what I'll be primarily indulging in this talk. Science is in essence negationary in pursuit, so please bear with me for criticizing several accepted paradigms. So, and then I would be saying a lot of I, me, my. Please see beyond that. I've been passionately pursuing this, so you will see why I talk a lot about me and mine. It's all my personal pursuit, and science is a lot of subjective viewpoints. You know, you will see that. I request you to bear with me at the outset, and then I would request you to keep doubts and questions at a later part, or if you're interrupting in the middle, I would expect the talk to go indefinitely, which is something that I would prefer not to happen because there are people who want to do something after a couple of hours. So let me start off with asking how many research scholars here? Please show of hands, please. 1, 2, 3, 4, 5, 6, 7. Okay. I know the professors. Okay. Okay. So some of the things that I put up in this is precisely what Andrew was talking about, how to challenge, how to question, things like that. So I'd like to tell you something about my own personal voyage also. I'm going to be 50 this year. I've been a professor. I've seen a little part of the world. I've worked as an independent researcher. I've been a principal of an institute. I've seen a bit of an academia. So I can share, there's a significant part of you who would also benefit. So please see what you want to absorb. Be selective. Before I start out, I wanted to ask you a simple query. So there are 7 scholars. So there's some chocolate here. I would like to retain the key for interaction. So I would just like to ask you, mitochondrial proton pumps, right? Research scholars. This is primarily. Do you know how many complexes are there in one mitochondrion? Anybody? Has anybody read my works? No one, right? No. Okay, good. No problem. You have read my works? Some of them, at least? Okay. So, anybody has any clue how many electron transport proteins are there on the membrane of a mitochondrion, an average? roughly 10, 100, 1,000, something like that. If you don't have, I'll tell you. There are approximately 10 to the power 4, approximate, to 10 to the power 5, depends, alright? So complex 1, complex 2, complex 3, complex 4, alright, all that. I'm directly jumping into the topic. This is just a teaser, please bear with me. There's no proper introduction here. This is just a teaser. This is just to make you a little prepared for what is to come. So we need a conservative proton requirement of 10 to the power 5 protons. Now, how many protons are there in a mitochondrion? Can you calculate if you have a pen? You know that one mitochondrion is approximately 1 micron long. Okay? So approximately 0.2 micron across. So it's a cylinder, pi r squared h. You know the volume, you know the Avogadro's number, you know the pH. With that, do you know how much is it? Anybody? The chocolate is for you, if you can. Okay, no problem.
8 protons.
How many protons? Yeah.
8 protons. Like through a cycle, there are 8 protons.
Yes, exactly. So you need, if there are 10 to the power 4 protein complexes, you need at least 10 times more than that protons you need. So, but how many protons are actually present? You know the physiological pH is 7.4. So if you expect mitochondria to work on proton pumps, you would expect significant amount of protons in the mitochondria, right? Now, if you calculate, basic calculation if you make, you know the number of protons that come out? If anybody says that, get a chocolate. Okay, no problem. Any idea? So if you make 6.023 into 10 to the power 23 into the volume of mitochondrion, it is 0.2 into 10 to the power minus 15, that is micrometer cube, 2 liters, and then 5 into 10 to the power minus 8, which is the pH, right? That will give you the number of protons. How much does it come? It comes to finger countable, 6 protons. So mitochondrion is practically aprotic. It doesn't mean that you cannot have protons for catalysis, but this membrane pumps require it for pumping out. So you need free protons. So this is the teaser that I start off with. My fundamental challenge to the existing Peter Mitchell's theory of chemiosmosis is based on very elementary mathematical calculations. A mitochondrion is fundamentally deficient in protons. With that, I am making room for criticism. Some criticism which anybody with a fundamental college level understanding of biochemistry can understand and appreciate. Right? So, now let me come to the next aspect. The word Murburn looks alien to you all, but let me tell you, since the last 3 years or so, it's not. Particularly in Marx Force, in the last 1 year, my papers have been published with the name Murburn concept. Okay? So, that's a SAGE journal. It's indexed. It's open access. Okay? It's a tradition of 10 years, almost a decade old journal. It's an American journal. So, I have ripped apart, I'm using the word. If you believe in critical pursuits, every single element of the standing explanation. The standing explanation has electron transport chain, Kaelin's electron transport chain, proton pumps, Peter Mitchell's chemiosmosis, and the rotary ATP synthesis of Paul Boyer. All these I have criticized and exposed for their mathematical, quantitative and qualitative flaws in the first paper there. In the second, I have provided quantitative, experimental and in silico evidence for my theories, proposals. This is a 35-year-old journal. It's got a 5-year impact factor of 5 or something. So this is a status update of Murburn concept. So at the very outset, I want to start off by imparting credibility to my talk. My works are published. It's not unpublished. It's been peer-reviewed. It has been published in decent indexed international portals. Not only that, there are people in Europe who really believe that this work is solid, and they have put it on cover pages of annual publications. Now, Biomedical Reviews has got a 30-year-old, almost 3 decades tradition. So that's the first paper where I challenged the Peter Mitchell theory, and this is the paper that's published now. This year it's the cover page article. Here I explain how cells produce heat by the same fundamental mitochondrial oxidative phosphorylation procedure. So what I want to say is they have been also cited in accounts of chemical research, you know. So basically it's not something marginalized or controversial. It's in mainstream. So now I'd like to present to you at this juncture a small video. It's a 3.5 minutes video of my work before I get into the crux of the work. So that basically gives you a snapshot of my work. So I have given you, now what I'll do is, I've given you a snapshot of my work. Now I'll take you through the basic scheme of my talk. First is the story of Morgan concept. Now, for that, the story of Morgan concept is my own story, right? I'm the author of that concept, so it's about me. So here is where, I'd like to share some of my experiences. I have been schooled in Kendriya Vidyalayas all over, so I had the ability to quickly adapt every 2-3 years. And 12 years of my schooling was in 8 schools. So adapting came quickly. BSc, I did it in Kerala. At that time, one wonderful thing happened. Kelath Murali Manoj, who became our president, he was the science and technology minister. He organized the national science level exhibition in Kerala. So what happened is, there I came to know about biotechnology, Department of Biotechnology. I wrote the DBT exam. Thereafter, I got into MSc, where I met Andrew. And here, I got introduced to biochemistry for the first time. And while I was writing my biochemistry exam in first semester, I tore my answer sheet, cried and ran out. Sanjeev, my biochemistry lecturer, asked me, "Why, Murali?" Because I said, I really didn't know what I was writing. I could get marks, but I really didn't know what I was doing. So this was what happened in my MSc. In my PhD, I did my work on lipases, and something personal happened. My friend died. It affected my life, and I thought of doing social work after that. And then in postdoctoral work, I went to France and worked on epoxide hydrolase. So basically, what this gave me was a strong inclination to work on proteins, particularly enzymes. I liked enzymes proteins because they interact with a wide variety of biomolecules, whereas genes primarily regulate things from the background. So slowly I got many of you research scholars, when you take up a subject, sometimes things come to you as a matter of choice, sometimes you're, by chance you're exposed, right? So certain things you see in my life too, I got exposure to certain things out of chance, certain things I stuck to as a matter of choice. Now, my specialization became enzymology. I think I would sit, it would be better for you, right? So, yeah. So, my specialization was enzymes. You see, reaction rates, collision theory, and then transition state theory, Fisher's lock and key, induced fit, Koshland's induced fit, Michaelis-Menten kinetics. These were my words. Basic classical enzymology. Well, I went to Lowell's lab in Urbana-Champaign and things changed. Things changed big time. I worked on the enzyme called chloroperoxidase. It's a heme thiolate enzyme. So it was discovered by Lowell in 1960s. He had the standing mechanism for it. And can I have a stick or something? Is there? It's okay.
You can use the one that is used for the AC in the corner.
Yeah.
Don't take it.
Yeah, that's fine. That's fine. That's just fine. So now you see, it's a heme thiolate enzyme. So it's fungal, extracellular, highly glycosylated. It's got a polar active site. So this is one enzyme that I worked with in Lowell's lab. Now this enzyme was very different from the enzymes that I had read about. It could work on such a diverse array of substrates that it was mind-boggling, So in the time that, in the next 1.5 decades, I also worked on cytochrome P450s that are also somewhat like chloroperoxidase in that they are heme thiolate enzymes.
Murali, may I interrupt for a second?
Please, yes.
You were talking about that nothing has come yet. The point is, you're spending all the time on talking about things that nobody will understand. So I request you to go and directly to your topic so we can understand what you're doing. There's no sense anybody can understand all those things except maybe God may do that. So please explain what your theory is, what we are here for, your topic. Otherwise, we'll be just sitting here explaining to you your stories. I'm sorry, I'm not the chair,
No,
but
I'm not the chair either.
whoever is the chair.
He's the chair, so, Murali,
I take your objection.
No objection. I'm telling you that if you want to communicate with people, you have to go directly and explain things. Otherwise, this is story. I can read hundreds of papers and look at the titles, no meaning to it. So if you want to communicate with the rest of the country or rest of the people in the world, please do so directly, rather than telling all the stories around. Nobody can understand this. It requires 3 hours of lectures on one thing that you're talking about. I'm sorry to be this way, but I am going to do that today.
Yeah, please. No problem. I heard you. I heard you. So, why I'm doing this is for you to understand what I'm trying to come to.
It will take 2 days to understand. If you keep throwing all these equations and numbers, there will be no understanding, I can promise you. From my I've taught 40 years in Urbana-Champaign, the same department of Hegel that you mentioned. And I have listened to him and understood what he's saying. But the way you are doing it, no understanding will come, at least to me. Maybe to the students understand
maybe
more.
only if I can sort of interject here. See, the Mitchell boy, we are a computational and simulation group, although we do have a base in thermodynamics and other things. So if you come to the Mitchell boy, what is the existing paradigm? And then questioning it. Now I understand that your reasons for doing this are also a side story, but we can keep that.
No,
as a
it's
side
not a side story. It's the crux of the story.
Okay.
Yeah, I'll come to it. I have no problem. I have taken your objection.
So what time have you given him? I mean, it will be take a whole day to come to this story when we go around beating bush around everything else.
So have you sort of typed it? Will it be in a finite time period of about an hour before we start and leave?
I tell you, this is what I started off with. When I started off with, I said, I have a talk prepared. I said, interruptions, I will take your comments and all that at the end. I have planned a talk for myself.
Nobody gives a lecture. I'm telling you. I've been to lectures at the Department of Biochemistry for years and years. But this lecture is not a lecture on any topic, because you constantly throwing things, papers here and there. It is absurd, in my opinion. I'm sorry, I've never said that ever in any lecture to anybody.
But I'll go a little bit in defense of Murali, because I understand since he's spoken about these concepts, people have questioned that he hasn't been able to publish them. So
let me please go on.
Yeah, move on.
There are 7 research scholars here. I need to tell them this is a fundamental concept that I've developed. Please bear with me. Okay? So this enzyme is a heme thiolate enzyme, and these heme thiolates and heme enzymes are common in mitochondria. Mitochondria also have heme enzymes. Let me come to it, Dr. Govinji, please. Okay? Please, I am trying to build a concept here. I understand.
But it is not building. As far as I'm concerned, I have no clue what you are saying. You're not going to the heart of the matter, which we are interested in.
Yes, yeah, I will come to the heart of the matter.
Okay, go ahead.
Please give me some time. Now, cytochrome P40s are another bunch of enzymes that I worked on later. I'm trying to tell you, my talk has 4 components. First is the story of Murkoon concept. Next is what is my problem with the existent paradigm that explains mitochondrial oxidative phosphorylation. Third is my explanation. And to come to my explanation, I need to take you through this voyage. Okay? So, as a research scholar, you would see a new system. This was the system that I saw. And when I worked on the system, conventional enzymes, they work on one substrate, one kind of substrate. Here you see these enzymes, they work on a diverse array of substrates. It's unbelievable. Same active site, how can so many substrates work on the same enzyme? So, and these were the 2 enzymes that I worked with. Now, in 2000, Lowell's I spoke to Lowell. I said, you would be given many projects to work, which would be funded. And I said, Lowell, I wanted to go back, so I would like to do something on my own. So he allowed me to explore certain aspects of the enzymology of that particular enzyme that he had discovered. Now, until that moment, what was the idea? Reactive oxygen species like peroxide, all those are very damaging to the heme enzymes. In this paper that we published in 2000, we showed that reactive oxygen species are not that dangerous. In this paper, we showed that this enzyme can turn over millions of molecules of reactive oxygen species before getting deactivated. So one perception that was prevailing in the pioneering lab was changed. That is a fundamental perception change. So, but then Lowell did not buy many of the ideas that I tried to usher in. So I had to publish that idea independently. Okay? So here I differed with Lowell and I showed chlorination reactions mediated by this enzyme, chloroperoxidase, works outside the active site. Now this reaction can also be selective and specific. What does selective and specific mean? If there are A, B, C, D, E, 5 substrates you give, this enzyme can pick, say, B from A, B, C, D, E. And now, if there is a substrate A, if there are, say, ortho, meta, para, it can work at one particular point. That is called specificity. Now, this is usually attributed to an active site reaction, is it not? Now, we showed a reaction that works outside the active site can also be mediated by a diffusible species, and that can be selective and specific. This is a paradigm shift in enzymology. That work was done in Lowell's lab, but Lowell did not agree to put his name on that. So I had to publish it independently in 2006. In 2006, I had gone back to US and I had also worked on cytochrome P450s, the enzyme system that I was trying to tell you before. And that enzyme system is found in the human liver. That metabolizes the majority of the xenobiotics that we consume. And that you can understand, xenobiotic is a molecule which has no prior evolutionary memory in the system. So how does the enzyme know that this substrate is to be metabolized? An active site cannot have the exact topography. So in that same system, whatever I had learned from the chloroperoxidase system, I applied in that. And naturally, when I was trying to work, my PI was frustrated with me and he fired me from the lab. Okay? So that's the reason why I have to tell you my story. This is the story of Morgan concept. Yeah, please. I rest the initiative. I will take the time. I will make the time. So, in this system, I once again showed that this was the first time that I showed reactive oxygen species are used by enzymes for routine metabolism. This is once again a paradigm shift. Reactive oxygen species are known as cellular messengers at the most. Experimentally I showed that if you take reactive oxygen species out of the system, that system doesn't work. What was the idea? I will tell you. Now I will tell you. In simpler system, I will show you how it works, and then I will come to the complex system of the cellular respiration. Okay? Now, then when I showed that, then Lowell also came around to accept my ideas. Then we published it's a JNS enzyme. He agreed that the enzyme has got multiple ways of interacting with substrates. That's why Janus is a Greek god, a Greco-Roman god, which has got 2 phases. So this enzyme can work at active site and can work outside active site also. So he agreed. And then over the next decades, I published in mainstream papers. You can see BBRC has got 80% rejection rate. I published the same paradigm. One simple observation, my dear scholars, if you are working, I found azide is a heme enzyme binder. You would know azide, cyanide, they are heme enzyme binders. Now, if you take azide and dilute it, you get the same heme enzyme activity increasing by 20, 30 folds. I thought this was something wrong. This was something wrong. I did it again. I showed it to Lowell. I said, this must be an artifact. The whole work experimental hands. When you work, when you get something, please believe in that. That's the reason why I'm trying to tell you this story. Anybody can read my works. It's out there. What I impart here is my personal experience. That's the value addition that I bring with this talk. Please bear with me. So, I published until 2016 painstakingly bits and fractions. The scientific community would not allow me to publish the whole story that I had built in 2006. So 2016, this fundamental paper was published in RSC Advances, in which I showed that one protein and another protein, the electron transfer was not done by protein-protein complexations, but it was done through an intermediary diffusible species. I showed it in this paper. Okay? These were experimental building to my theory. And then in the cytochrome P450 systems, including Andrew, we collaborated. We published this. Earlier the theory was that the two proteins reductase and P450, they were stationed on the membrane. The transmembrane segments met together and they helped electron transfer and all that. We showed it was not like that. They were published in mainstream papers, you know. So with that, we built the Murburn concept. In 2016, finally, I went to US. I was not able to publish my work. I went to the Gordon Research Conference. There I met one wonderful person, Gabriel Cruciani. He was a keynote speaker. He was speaking, and I got up and asked, and he said, he was simulating how the molecules go into the active site and all that. I said, don't you think, Dr. Cruciani, this is a little bit of a stretched exercise? He said, well, you know what? I do think so too. I am doing it because people expect me to. He said that. And then I told him about my works. I said I have got another theory which can explain how these liver enzymes can metabolize so many diverse xenobiotics. And he said, wow, this is wonderful. So he helped me publish this paper. This is an in silico paper, wherein I coined the term Murburn concept and introduced this work. Okay? Now, Murburn means muod burning. Muod is closed. Burning is a reaction which involves radicals, oxygen, the ordinary reaction, right? So that's how it comes that. Or it can be mild unrestricted redox catalysis. So in this scheme, diffusible reactive oxygen species are an obligatory requirement. That's the most salient part. There is an enzyme. If this is a substrate, the enzyme reacts with the substrate through a diffusible species. So that's a big paradigm shift in enzymology. Now, and finally, I published the work in Frontiers in Pharmacology. This is the leading journal in pharmacology, open access, okay? In open access journals. So, after about almost 2 decades of struggling, I was about to give up when it was published. So, now, what is the mechanism? Now, here, I am trying to tell you about a simple reaction system. You know, the cellular respiration has got complex 1, complex 2, complex 3, complex 4, complex 5. So many complex proteins. Each complex has got so many redox centers. This has got only one P450, one heme enzyme, and this has got one flavin enzyme. That has got so many flavin enzymes, so many heme proteins, cellular respiration. I am saying this so that you can understand. Please be with me. Here, what they had thought, there is a flavin enzyme. This is the heme enzyme. This is the flavin enzyme, reductase. What they had said is, the substrate needs to bind to the heme enzyme. And then the reductase comes and binds to this complex, reduces the protein, and then oxygen comes and binds. So, oxygen activation occurs at the heme center. That was the earlier theory. And the substrate needs to bind to this enzyme for the whole catalytic cycle. So, I challenged this theory. I said, no, reductase activates oxygen, superoxide is formed, which is stabilized by CYP, and that reacts with the substrate. Very simple theory. This theory is multi-molecular and cyclic and requires complex recognition, multiple protein complexation and all that. In reaction kinetics, this cannot make any sense. So this thermodynamics I will not get into. There is no protein-protein interactions. Only substrate is required in the last step. Very simple reaction scheme. But reactive oxygen species is used. Okay? Now, in the mechanistic level, that's the overall cycle. In the mechanistic level, substrate comes and binds here, and then it has to be moved into the active site. First is lock and key, then induced fit, then the catalysis. In my scheme, nothing like that. The substrate can bind anywhere. Anywhere it can bind, and then the reactive oxygen species that is stabilized here, it can come and bind and react with the substrate. Now, there is a significant amount of stochastics involved, probability involved. This will not abide by Michaelis-Menten kinetics. So, now, so what is Murburn concept? It is a molecule, it might have a redox center. Any molecule can act as an activator, additive or a substrate, and an ion can be present in the medium. Now these three can have interactive dynamics. And the time scales may vary, there will be a stochastic scheme involved, and you can get constitutive controls. There are thermodynamic controls, inbuilt thermodynamic controls into the system. There will be variable stoichiometry, there will be it's a fast discretized process, it is not a centered process like all conventional kinetics. This is a very different system, it's a totally new paradigm. And this is the paradigm of Murburn concept. And this is how I came to Murburn concept. And now you will see what, please don't get into the text. Please don't get into the text. Please don't get into the text. This was one thing I had put in the earlier part of the slide itself. When there is too much text, please look at me. I'm the beautiful guy here. Okay? So I have already explained the heme peroxidase system with Murburn concept. The microsomal xenobiotic metabolism system with Murburn concept. These two are explained. Now you see, they are such one enzyme, one ROS, one ion. This has got two enzymes and then it has got three substrates. Now you see, this is the huge reaction that we are going to come to, which is the cellular respiration. Here, what in the two enzymes itself, they had said oxygen activates heme. I said it is flavin activates heme. Okay. Similarly, here I am going to change the whole paradigm. It is going to the whole thing is going to change. In this system itself, they thought that peroxide was inhibiting the enzyme. I said peroxide was not inhibiting the enzyme. Peroxide was getting depleted, which is why the reaction was stopping. So perceptions were all wrong. Experimental scientists can give new perceptions based on their observations. That's what I came to. Now this is the third system. Now you can see, finally, where has Murburn concept been applied? Now this concept has been applied to explain the atypical kinetics, non-Michaelis-Menten kinetics that you see in several enzymes. Okay, in redox enzymes. You will get kinetics like this. They don't buy the Michaelis-Menten paradigm. My mechanism can explain this. Then ecological, the heme peroxidases, it has been applied for explaining the halogenated organics and lignocellulose recycling. This has been already applied. Now you see these diverse substrate molecules. Earlier, CYP2C9 was an isozyme that binds to all these diverse molecules. Do you think it will have the ability to bind to one site? Now my mechanism can explain this. So in xenobiotic metabolism, it explained a wide variety of phenomena in the physiology. Okay, let's not go into that now. The point that I showed that is, it has been used to explain a wide variety of physiological observations which Michaelis-Menten and the earlier theories could not explain. That's what these things explain. Now, this is the paper that was published in Dose Response. It is the leading journal, open access journal, for dose responses. This is the physiological application of my theory, wherein you see all receptors and all enzymes, if you increase the concentration, what happens? Concomitantly the activity would go up, right? That's what you expect. In enzymes and receptors, you increase the concentration of a molecule, the activity should go up. But in certain cases, when you put a molecule at a very low amount, you get a higher activity. That was not explicable in science. Since my theory invokes intermediacy of radicals which are stabilized at low concentrations, my theory can explain this. This is a scientific fact. It has been published. So, Murburn concept has been used to explain a wide variety of physiological, ecological and enzymatic paradigms. That's the point that I am trying to say here. So, Murburn concept is a fundamentally different enzymatic paradigm view. That's what I have tried to explain in the last half an hour. Okay? Now, with the interruptions, that is, now let us come to the crux of your talk. Sorry, please Dr. Govindji, now I hope that your interest will be back here. Now for this, because I know that people were from diverse backgrounds, that's why I had to give this enzymology test.
Keep explaining, just keep explaining the data and thing. You're just constantly talking about things that are not related to the...
Dr. Govindji, I have had this talk purely for you. Please allow me to talk.
So please, go ahead and
thank you. I'm making the talk. I'm making the talk. Please. I'll come to your field also, please. Yeah. So now, what is a contemporary theory? The contemporary theory is you have on the inner mitochondrial membrane, you have complex 1, complex 2, complex 3, complex 4, all that, and then the electrons are put in, and as the electrons go via the complexes, protons are pumped out. Okay, this is standing paradigm. Now here is the explanation in a different way. They are the structures of complex 1, complex 3, complex 2, complex 4, and this is the complex 5. These are the components of the electron transport chain, and these are the equations. I will not go into it. This is not required. But you see that there is no connection whatsoever chemical with these electron transport chain components and the ATP synthesizing component. There is no connection whatsoever. There's no connection whatsoever. Please note that. Okay? ATP synthesis is a chemical reaction. There is no connection whatsoever. Protons are supposed to come in, and this is supposed to go round and round and make ATP. That's this theory. Now, how does this look on a machine logic? Let us see the machine logic. Now, if you see in terms of machine logic, it resembles like a dam where you have the water coming in, like the protons, you can equate, and the complex 5, which is a turbine, it goes round and round and makes ATP, which is the equivalent of electricity, right? The dam. Only thing is that ETC is the one that puts the protons back there. So that component is not there in the dam. We use the gravitational gradient, to work that way. Here, if you take a functional analogy in car, you can say the fuel is burned by the engine and the alternator recycles into the battery. Similar logic like the chemiosmosis. Right? These are the two comparisons. Now, what is the problem with this theory? Okay, other than first, let us say there's no proton in the mitochondria. Let's keep that. Let's talk about the evolutionary aspects first. If you're biologists, you will see it's a vitally deterministic scheme with irreducibly complex components. Each one needs the other. 5 proteins, none of them work independently, everything needs the other. Okay? And it's all deterministic. Circuitry, everything has to be there. And the losing end gambits. If you play chess, you know what a gambit is, right? You give to take. Proton pump has to work, something has to throw out, the energy has to be thrown, then to be harvested later. It's a gambit. How can such a gambit form at an evolutionary stage? That's the question. Then, this scheme has only about 40% efficiency. Substrate level phosphorylations, if you study glycolysis and all that, that have 50% efficiency. Why should an evolutionary system choose, I will come to the calculation later. This has got a very low efficiency. Why should evolutionary system choose a low efficiency system? Then, Dross formation in mitochondria is not explained. Why? Why Dross formation in mitochondria? There is no explanation. Why didn't evolution do away with Ross? Why couldn't they do away? Then why is complex 5 an ATPase? Of all things, complex 5, when you isolate it, it's an ATPase. It hydrolyzes ATP. Its function is to hydrolyze ATP. Why should it be an ATPase? Why is it not an ATP synthase when you isolate it? Then, why animals with higher metabolic rates die quickly? If the evolution is geared to have better metabolism, why should animals with higher metabolic rates die quickly? This simple evolutionary argument. And in terms of oxygen's role, oxygen is just supposed to bind to complex 4, cytochrome oxidase. It has no other role in the contemporary theory. It is just to make water. No other role. The electrons all reach their complex 4, it just binds oxygen, receives 4 protons, 4 electrons to make water, 2 molecules of water. No other role for oxygen. Okay? And if you make simple calculations, you will see oxygen has a coverage of approximately average at least 10 to the power 2 angstroms per microsecond. The electron transfer rate is approximately, if you see the electron transfer rates, oxygen will be there at every instant. All the deterministic circuitry that the current scheme seeks, it cannot work. Oxygen will shunt every single step by simple question of the diffusibility and access of oxygen. This theory cannot stand. What oxygen role? So, how can the deterministic ETC work in presence of O2? Why does oxygen mess with anaerobic systems? If electron circuitry was so specific, why in anaerobic systems? Why can't they live in the presence of oxygen? Why in the ETC research we can put in and receive electrons through so many probes, man-made probes? So very clearly the deterministic electron transport chain is just a whim of some people, nothing else. So stoichiometry and additive effects. The current deterministic scheme seeks very clear-cut stoichiometry. How many oxygen molecules are taken for how much phosphate, how much hydrogen, how much protons for how much phosphate. It varies. Different researchers all through the 4 or 5 decades have reported different numbers. The numbers vary. And uncouplers, the current, one of the biggest successes of Mitchell was to say that dinitrophenol is an uncoupler. It keeps flipping and flopping. Why should it flip and flop? When a proton cannot go across the membrane, this is supposed to piggy ride the proton. This has got nitro group as positive, negative charges. This is a much huge molecule. When this can go across and all that, protons cannot go. It is just a whim. It is just a whim. It is not supported by any kind of data. Now, next, architecture, structure. No modularity. There is no modularity in mitochondria. You would expect the, all these components to work in certain modules packaged together. There is nothing like that. It's just one membrane, outer membrane, one intermembrane, and then molecules distributed on the surface. That's it. And the ratio, you see, the flavin enzymes, complex 1 and 2, they are very low compared to the heme enzymes, which is high. And that's the same system in my microsomal system. If you expect a 1:1 complexation and the circuitry that you expect in the ETC scheme, you expect a correspondence. Here it is not. In the microsomal xenobiotic metabolism, you see reductase is 1, whereas the heme proteins are in hundreds. Same thing in that system. So this doesn't agree with the electronic circuitry. Then the projections of complexes 1, 2, 3 go deep into the matrix, pendulous complexes. Why should they be? It doesn't explain. See these complexes, why should they be like this? The distribution, nothing. Then Complex 3. Complex 3, there is no explanation whatsoever. This whole thing, puppy, that is here, the current system has no explanation. This has no role whatsoever. Okay? And these things, there is no explanation why these things should be there like that. Now, if you take the ETC, if you see my critical analysis paper, you will see the complex 1 and complex 3, if you see, the energetics do not support the proton pump. It is a gross theoretical error. The energy required and the energy that is working at that center, they don't agree. There is star proton deficiency in the overall reaction system for it to work in a closed scheme as that is needed. So you need, in this scheme, you need 54 electron transfers in batches of 1 or 2 electrons to make 1 molecule of water. 54. It's like it is made to make 1 molecule of water, 54 electron transfers steps. Doesn't make any sense. For each of these, now there are 15 complex interactions that needs to occur in that. 2 steps of 10 to the power 4 per second and 10 to the power 2 to 10 to the power 3 per second. Each one of that 15 intermolecular electron transfers, they need this. And the overall electron transfer rate is 10 to the power 3 per second. Now if you have 10 to the power 15 steps in which there are 2 steps each of these kind of things, how can you get such a rate? It is quantitatively unimaginable. Okay? Now, I will come ETC, you see this. Electron transfers are supposed to occur here. Proton pumps are supposed to occur through this. How? And this is supposed to occur in microseconds. Proton pumps are supposed to occur in milliseconds. How? No reason. Just people think it is like that. There is no evidence whatsoever. Now, if you imagine that there is a proton pump and it is something like that, then you would imagine the scheme should be like this. Coenzyme Q is supposed to bind here and the electron is supposed to come from NADH like this to here. It's supposed to take here. The better scheme should have been coenzyme Q binds here and then the electron comes through this way. As it goes through the redox centers, the proton can pump out. If this was the structure, we could say, okay, this is not the structure. And if you analyze it deeper, the distances are too far and the redox potentials, you expect electrons to go from negative to positive. The values are very, very counter against that. You have minus 250 and then it is going to minus 300. How can the electron go like that? It cannot go. It is just whims. It is against the fundamental thermodynamics. Then, complex 3. In this, if you see, this is one of the smartest cycles invented, but the most improbable ones. You need CoQ, how many molecules to interact at the same time, Cytochrome C, coenzyme Q, both oxidized and reduced at the same time, they should bind to one protein. 3 different molecules should bind at 3 different sites at the same instant. And you know what? How this mechanism is? Now, if you have 2 marbles, you take it, you roll it down a mountain, and then one molecule goes there, and the other marble goes and stays on top again. That's what it is. The electrons go to coenzyme Q and then come back to explain this. This is just another fancy, just invented, just to meet the requirement of the cycle. Nothing, there is no evidence for this. And then, very simple thing is electron transfer between two hemes. If you take the anaerobic electron transfer rate, it comes to less than 1 per second. If you take aerobic, it comes 1000 per second. So what does it mean? Marcus outer sphere electron transfer theory is what is supposed to be operative here. Electrons jump. Oxygen is required for electron transfer. That's what is shown even in complex 4, one single protein. See the electron transfer rate difference, 1,000 folds. And you see, my theory had explained, you know, if you know Michaelis-Menten simple kinetics, Km, Kd.
I hope you are understanding what he's saying.
Actually, the numbers are a little beyond what I know because I don't work in this area, but Murali, take this.
No, the problem is that you are putting in amount of work that is for 1 month and not explaining steps, but you are just attacking and saying this doesn't work, this doesn't work. So you go ahead. The point is you are not convincing me of anything so far. I have not been convinced of a single word that you have stated because of the way you are presenting your talk. I'm sorry, I've never said that ever in my entire life. And you may take my PhD away, you may take my professorship away, whatever you want. All I'm trying to do, being very honest to you, is the way you're explaining, this doesn't work, 2 cycle is like this. No, it is not. Who is going, that even one sentence means at least an hour of explanation why. And you think what you are convinced yourself, you think everybody else will be convinced instantly. So it's a waste of time. That's all.
That criticism I have to accept because of the broad audience. See, the thing is that it would be nicer if you can give a definition of what this is.
Why not explain at all anything.
So the paradigm that exists, what is there, why it does not work, and your solution with some data if it is there.
So your way of explaining is you're only talking about in a way that only you can understand and you write a book.
I have this being recorded
Fine,
as
that's
per your
great.
request.
That's wonderful.
No, this is being
It's not going to help me. I will not show that to anybody because I know that hundreds of people that I know in my field, in biochemistry and biophysics, will not understand a thing the way you are presenting. That's all I would say.
Professor Govindji, I'm just keeping it for posterity. At least.
No, fine. That you can keep it as you like. I'm telling you.
Can I go on with my presentation?
You
Yes.
can, but also there is the concern on time. So basically, if you follow
The
this.
time, I would have made my time if not for these
Okay,
objections.
here's the thing.
No, that means you were never taught at the university, you were never taught anywhere that you do not know how to deal with a talk. That's all I will say.
Murali, if you can, just focus on, see, we don't need justification that you have published it in X, Y, Z and all
That's
that.
a waste of time. Hundreds of papers you are showing, your slides. Everybody knows that. And it's total waste of my time here listening to that when I know the papers, you have a list, everybody can see
Can I
that.
suggest, I'm not an expert, maybe it's a suggestion. If you can sort of wind up your talk, then we can ask some questions, maybe simple question that might make certain.
All right, those of you who think my talk is a waste of your time, please, I'm sorry.
No, it's not a waste of
I mean, what the hell?
Murali, just focus it in the following flow.
No,
Will you
wait,
I'm sorry.
please, wait. I said this, okay? Now, I want a very simple thing. Please listen to my talk. Let me finish my talk, okay? You gave me your interruptions. I said this very clearly. Let me make my presentation, okay? Let me make my presentation. There should be some amount of decency in you people. Even if you don't understand.
Okay, the point is that the relevance of what we are trying to understand is not coming across the way you're presenting it. So see, the way that you do this is Mitchell Boyer says this, we know this from the textbook. This is what I think is wrong.
That's what I'm doing now.
I know.
That's you said,
Wait a
nothing.
minute.
That's what I'm doing.
I know, but it's coming in a little too strongly because you're saying this doesn't work. Now we don't know what this is. So you see, the Mitchell Boyer.
So that part comes later.
No,
That part comes later.
Well,
That
point-
usually, you know what, Dr. Goenji? That comes after the talk. You don't do this to everybody's talk. I'm challenging your lifetime's work.
No, calm down, Murali, it's fine.
Listen, nobody is challenging anybody's word. The important thing is right now, please decide how many minutes he has
Yes,
in this
actually that's
talk.
the point. Murali, how much time will you take to finish this? Because ideally we normally have a talk of about 1 hour. We
Max.
will have more discussion, right?
Okay.
We started.
Okay, let's go to a talk slide that we would understand, right? I would not talk anything else. Let's go to the talk that he would understand. You understand this, Dr. Goenji?
No, don't ask me questions. I'm not going to be judged and failed by
You
every
judge me, Dr. Goenji. You try to tell me that this is your work, Z-scheme. Let's talk about this. You game? You game? Let's talk about this.
No. You don't waste your time in saying silly things. You just talk about what you want to talk about.
Let's talk about this. This is something that you will understand. This is the scheme.
Yeah,
this is
we are
advocated
stupid
by
people.
Dr. Govindji.
Now listen, this is the most ridiculous way of speaking. I've never ever in my life listened to anybody. in this-
Nobody else is complaining, Dr.
Nobody will complain to you.
I'm sorry, but
I'm the only one who.
You are his
not
prodigy.
is anything. Please don't say
I
that.
think,
First of all, I think you're trying to cover too much ground in one
But no,
talk.
useless.
I would have preferred if you had stuck to one thing and
Look.
shown some supporting data from every angle.
Let me come to that, na.
When will you come tomorrow? You spent 1 hour already.
No, that 1 hour, 15 minutes तो आपने ले लिया, Dr. Govindji.
No, we started 15 minutes late. Murali, now let's take this through. Now look again, Professor Govindji has proposed a lot of photosynthesis. Not everyone in this audience does. So just for the, define what it is and define it without attacking it. You know, we don't know what you're attacking.
No, I am going to attack.
And they have a
Listen,
My talk is going to attack.
But listen to me. Listen to me once.
Yeah.
The way you're doing, you are destroying yourself constantly. If you only attack and do not explain what you have to say, it's useless. So your job should have
Andrew,
been.
did you not tell me to talk about what is the problem? That's what I was doing. Why did you have a problem with that?
I haven't understood the problem because you jumped through it so quickly. You're just attacking it. This is why it is not. This is
So
why.
then let me talk now. What you did not understand, you ask me. I will tell you.
So go ahead with the photosynthesis.
I will tell you.
No, Murali, go ahead with the photosynthesis.
Yeah,
We
let
can
me-
argue that straight away and then let's
Talk about photosynthesis, something that you will understand.
Bottom line is you're questioning the substrate specificity based on the lock and key induced fit versus a diffusible moiety. We need to see what data.
No,
has
this
been
was a
done
very
with that.
simple thing.
No, that is what. Now show me
No,
these
see,
principles.
when I'm giving a talk, usually I have been, I presented a talk in QSAT before coming here, okay? And there, this audience sat jam-packed, okay? Nobody except one person keeps on complaining, okay? It's a very clear-cut thing. These people didn't have, no wait.
No, I have to also question this because see, we have a standard in India. Professor Govindji, give me a minute.
Because if he keeps attacking.
No, you have attacked me, Dr. Govindji.
Yes, you have to learn to take it as criticism.
I have no problem. I was smiling all the way till now. He's getting up and going.
Wait a minute. Murali, please. Just define now stick to one system like photosystem. We've got the basic idea. I have some ideas I want to question you with because I come from the area of proteins and I think that the one is substrate specificity is very much.
No, let's just. I have got the authority of photosynthesis. Let's talk about something.
That and also
Just,
phytochrome with substrate specificity.
if anybody is interested in my talk, please stay back. We will talk if Dr. Govindji really believes in his work.
No, Murali, please.
Yes.
Just take
This is my question.
No, Professor Govindji has not just a standing within the university, but globally on photosynthesis now.
His history and the future.
But it's fine.
His history and the future.
Murali,
This is being recorded.
I think
No,
we need to-
no, you cannot stand. Andrew, you also took the
I
same
want
stance.
you to define what you understand by the photosynthesis.
Let's start
What
the
is
talk.
wrong with
Resume
it?
the talk.
Thank you. That's like
And maybe we get time.
Yeah, you should give me a chance. I'm not a nobody here. I come here spending my time.
Yeah, sure.
Murali, I
Mazak hai?
want to add to the question.
No, I thought I'll not lose my head.
Yeah.
This is pushing me. This was a strategy.
No, go to the PS. Where are you going? Go use the photosystem and move on from there, no?
No, this is the last slide. I thought I'll discuss it in a proper way. This is no. You have a talk. Somebody presents. You attack that talk. What do you after a particular point you will use the head here. Now, what is the current understanding of photosynthesis?
Right. Let's start.
There are two photosystems. Photosystem 1, photosystem 2. Now, if you have 1957 Emerson found something fundamental. Let's talk about the paper that you did. Photosystem 1, if you put photosystem 1 alone, you get oxygen. Photosystem 2 alone, you get this much oxygen. You charge them. Both, you get much more than what you get added up. Yes? Right? Now, they put it in series. Right? Photosystem 1 and 2, series. Anybody with a basic amount of electronics would know
That's exactly the point is that your job is not to explain, but anybody, I mean the whole world is crazy, whole world should be thrown out of this world.
Now, why don't you just sit back and take it?
No,
what I
I
have to
will
say?
not.
I think the question.
You are not staying with the points that nobody ever has ever given a talk like you do, because you're not interested in communicating, you're interested only in attacking.
Yes, I am interested in attacking.
Yeah,
I
so
don't
then
want to do
I
that.
should not be here.
No, no, but the point-
Why are you such a touch me not when your work is
No,
being
you
attacked?
can't touch me on. The way you are speaking is the most outside the world way of saying, giving any talk. That's all.
Look, no, wait, let me see. See, you see, you have to change the attitude also when you're discussing your thing. Present the data and let us make
This is
our
a
point.
data. This is a simple
I
thing.
know. So don't say that anyone is an idiot, doesn't
No,
understand.
anybody would. I would like to
Here's my
say.
question. You have series, you have parallel. Define what is going to happen with the series, what is going to happen.
Now, if you attach two elements in series, what will happen?
It's
The current will go lower. You cannot explain. It has to be parallel, which is my system. Very simple. It cannot be in series. Second thing, this negates the Z scheme. Simple thing. Now, very simple. And now,
Again, it's the same word using very simple. It's simple to you, but not simple to anybody else in the world.
it is not simple
Let's
to you.
take the whole problem that you said that series current will go down. Why should it go down? Because it's additive. You can actually help. You're looking at it.
You're not explaining.
This is the equations in series and parallel. This is the equation. You find out it's elementary.
No, you're looking at the
It has
electron.
been disproven.
Show me some data that you have done to really support your theory versus the other, because we have not read all the papers, and therefore I am looking for some hard data which is supporting your theory, and just stick to maybe one smaller
What
thing.
is
We are all
only the
not so bright.
Dr. Tiwari, I'm talking about theory here. I'm talking about theory.
Yeah, but
Theory will-
I'm a mechanistic biochemist, biophysicist.
That's fine.
Okay.
But it
Now
has
it's
to
a
be
very
supported
simple.
by some
It's a very
papers.
simple. It's a very simple elementary logic.
No, it's not a simple elementary logic. I'm
It's
sorry to
simple
say that.
elementary.
No, I am dumb. You should take away my PhD, remove my professorship, because the parallel scheme was Daniel Arnold's scheme, and it was proven clearly by Joyce and Ames that it goes in series. Now, if you have an argument, you have to write a whole paper and send it to 10 people, and then we read it and we see what you are saying. In one sentence, you are totally trying to condemn everybody, everything that exists in the literature without any evidence, without anything. So basically, that is my problem with your talk. Now,
No, that's okay. Why shouldn't people do that, Dr. Govinji? Why shouldn't people give a talk like that?
Problem is-
Why shouldn't? Isn't it a free world for a scientist to talk like that? When did that stop in JNU?
No, by all means, but you have to defend yourself. The point is that
Why am I not defending? I'm standing here.
you are attacking people. You're not defending yourself.
I'm attacking ideas. I am not attacking
I'm
people.
questioning the fact that when you say in series that you're saying it's going to reduce. Why should it reduce? You're using it.
Yeah, but the equations are here.
no equations will not explain a thing. You have to explain the goddamn thing if you want people to
No,
understand.
okay. If it doesn't explain, you tell me how does a
Don't ask us questions.
I will answer that question because I.
you can stand and cut me and I
No,
cannot
no,
ask you a
no,
question.
no.
What is this? Isn't it a scientific interaction?
No, it is not.
Use the principle of amplification done in series. Amplification in series. Now see, I don't know what circuit you're using where you say.
Very simple, two elements connected with
No,
one
no.
powering element.
A principle of amplifiers is that you have something that is amplified in a series. Amplified. Now we are talking about amplification here also. It's a simple English translation. that I can-
So
now why
what
does it
happens?
reduce?
What
Now
happens
see,
in
this is the
application? More
example that I'm
current.
hearing.
Current should flow.
No, you're using current. Why should it be current?
It should be current because here we are talking about current electrons because we are getting more oxygen formation. Oxygen formation is directly correlated to current. Only current. We are talking only about current. We are not talking about anything else.
When you're talking about it using a concept
But
of
you are
electronics in
using
a
the
circuit.
analogy of resistors, but if you are using the analogy of conductivity,
Conductivity, this is
then whole thing will, the first
no.
postulation will be correct.
Conductivity is what I'm talking about. Conductivity and capacitance.
Inversely proportional to resistivity.
Yes.
Then
So,
the first one will prevail.
Resistivity will increase, conductivity will decrease, na? So that's what. So that's why parallel should be. So that's the equation here. Series में नहीं होगा, parallel में ज़्यादा होगा. You just imagine. No, you just imagine. Electrons have to go in one track. You are giving multiple tracks to go from point A to point B.
You are considering this as an equivalent to resistance. You are considering that.
No, it's not resistance. It is conductance. Conductance and capacitance. We can by impinging photons, you can get electrons out. That is capacitance, equivalent to capacitance. And other elements are conducting elements. Okay. Now you just imagine simple. You have point A to point B. You have to transfer electrons. Now you have got 2 points, 2 elements. You have to point 1, 2, 3, or you have 1, 2. You go like this. You get more.
Maybe 2 of you can, 3 of you can discuss this later because it is making no sense to me, and therefore please finish whatever you have to
Oh, thank
say.
you. Can I go to my talk?
But I mean, when?
Better wind up so that we can have a Q&A
Yeah.
on this.
Yeah. I would just like to present. I'm coming to that.
Murali, we won't be able to go through all these slides.
No, wait,
Just
one
give me
second.
focus on what you're trying
So
to say.
So KD KM, this is where I was. Now, the KM of complex 4 comes to 0.001 millimolar, but the KD is only in millimolar range. KD and KM are not like that. KD right? This is the equation. So Km can only be bigger than Kd. This doesn't make any sense as per the theory. Okay, so complex 4 interaction with oxygen is not at all explained by the current theory. This I had explained in my cytochrome P450 system. So the energetics is, see, now the game is, I cannot explain to you, the time is gone, right? So I'm not going there. Very simple. Let's make this slide as my slide. Okay, very simple. Complex 4 has 10 to the power 7 times more affinity for ATP than ADP. Complex 5 has 10 to the power 7 times more affinity for ATP than it has for ADP. In mitochondria, you have at least an order higher concentration of ATP than ADP, usually working. You tell me, how will complex 5 be making ATP in physiology?
So are you saying that all the transporters which do active transport, so I'm taking that analogy, that active transport of anything against the concentration gradient of anything also requires input of energy, and this is a kind of a transporter also. So you are also saying that these transporters are not able to do
No, I'm not saying that. I'm saying complex 5, I'm coming to my explanation. Complex 5 does have very valid role in ATP synthesis, but it is to bring in protons. That's how it's that's why it's a coupling agent. It is not the ATP synthase. ATP synthesis are the 4 complexes. This brings in only protons. I will show you now. Let us go the philosophy and all. I wanted to see, our Professor Nath also doubted this. There were so many. Slater was the man who had called for thinking beyond chemiosmosis. I'm not the only guy. There were so many people made him an outlaw.
that is what I'm trying to understand. If you're saying the other 4 complexes are the ones which are involved in ATP synthesis, could you please explain?
No, I'm coming to that. That's the newborn scheme. This is the scheme. This is the scheme.
No, that's fine, but tell me in terms of...
Yeah, I'm coming to that. Yeah. Now here, what is my scheme? My scheme says that the transmembrane portion of these proteins, they help the protein to be embedded in the membrane. And the cytoplasmic pendulous part, they generate reactive oxygen species. Now what is those reactive oxygen species? This part bind ADP. They bind ADP and they generate reactive oxygen species. Now they bind ADP, generate reactive oxygen species. Reactive oxygen species attack ADP and phosphate and then they couple. It's by a radical reaction.
So the structures are known for all these complexes.
Yes.
And they have shown that they all have an ADP binding site.
Yes, that's what my work is. I have shown where the ADP binding sites are on these proteins. That's what the data is next. Now this is the whole scheme. This is my scheme.
No, but is that a computational analysis? Or
Yeah, docking analysis supported by experimental data. Wet lab experimental data.
This is what we have been asking for, that you should.
No. See, Dr. Tiwari, I need to build my pace now. I have to say my story. When I introduce a character, you should allow a person to introduce a character. I'm not a small baby making a talk here. Yeah, clearly. I have made presentations in so many places. It's not this is not the first time I'm making my talk. Okay, please let me explain what I'm saying here. Now, here is the steady state perspective. Here is the simple standard reaction chemistry. All these complex 1, 2, 3, 4, they bind to ADP. They have oxygen axis. They make ROS. So they make ROS. They generate such species. They condense to form ATP. What does complex 5 do? This is a proton deficient system that regulates protons and brings protons in. Porters and porins. Porins put water out as water is formed and ATP is taken out, and uncoupling protein, they make, they help make heat. And there is a background level of when the ROS react among themselves, they make heat. Now, these are the reaction chemistry. I will not go into that. People would say they would not understand. Now let us go into what are the evidences? This is what you want, right? Now, very simple. In the mitochondrial xenobiotic system, same with low amount of flavins, high amount of heme enzyme. Same kind of system, same kind of electron donors, NADH, NADPH, only difference. You see the thermodynamic parameters of oxygen consumption, the inside locks in the system. The experimental variations, the kinetics, very similar. The proteins distribution, all the systems, membrane proteins, everything is very similar. Then I have shown you take ADP. What more do you want? Take a test tube, ADP, phosphate, put superoxide, you get ATP. What more do you want? What more do you want? And this has not been done by me. It was also shown by Mailer in 1990 that when she took mitochondrial suspension and she put xanthine and xanthine oxidase, which is known to generate superoxide, she found ATP formation. In a chloroplast setup, they did the same thing. They found ATP formation, which was inhibited by SOD, which takes away superoxide. It's a one electron paradigm. Now, this is conclusive to me. Anybody buys it or not? Very simple. It was not for me to unravel. See, very simple. 4 things. This is a graph taken from Nichols' paper. He is a standing, leading researcher in this area. Now, it is known, more NADH and more oxygen you give to mitochondria, you get more ROS. Directly proportional. More NADH, more oxygen, you get more ROS. Complexes 1 to 4, all of them are known to produce ROS. increase in ROS, increase in TMP. Transmembrane potential 180 millivolt is minimally required for ATP synthesis to occur. So without ROS, there is no ATP synthesis in mitochondria. This is conclusive data. Very importantly, there are 30 known 1 electron agents. Why do we need, the current scheme is 2 electron. Why do we need 31 electron agents in the overall respiratory chain? It's a 1 electron paradigm. Nature of oxygen, it's a diradical. Why do we need oxygen? Why did oxygen become the elixir of life? Because it's a diradical. Radical reactions are fast, 10 to the power 10 per molar per second. I will give you the distribution of proteins, randomly distributed. Mine is a stochastic scheme. It works in stochastics. The structure of all proteins, the bulbous complexes. This thing has no other role. Complex 3. It has ADP binding sites. That's what I have shown. Why should it be there? The current explanation has nothing. Here you see, this pendulous part, it has oxygen cavities to access the all FES centers. Why should the FES centers not be buried if the electrons are supposed to go without becoming ROS? Very simple. It is to make ROS. It is deliberate. This thing, it has got 9 FES centers. There are some centers that are not even in the path. The current explanation does not give why the redox centers have suppose if you have a simple slide like this, minus 350, minus 300, minus 250, it's good. Why should there be a disparity in the redox potential? Why should the distances be far? Deliberate ploys by nature to make ROS. Why ROS? Because ROS can couple. I have shown in the chloroperoxidase system, it can insert chloride ions. It can insert phosphate also. Same logic. You see all the structures. Cytochrome C, very simple. You search your cytochrome C database. Or the ligand spheres are only conserved. This surface is not conserved. Surface is changing. Current theory requires 4 molecules of these to go one after the other to give electron to make water. Why should it make water? There are no proton pumps. There are no protons. The complex 4, complex 5, it has 2 ADP binding sites, not 1. And as per it goes round and round, changes. I have clearly said 10 to the power 7 affinity. It cannot. It works against all concept of thermodynamics. It's just because Peter Mitchell gave that theory. See, I would like to tell you one thing. When Slater's theory was in prominence, Paul Boyer proposed phosphohistidine as the intermediate that even Mitchell, first when he proposed it was proton, then he said is the electrical potential also. That's another violation of thermodynamics. I will tell you, if you are interested, I will get back to that. Now I have supported my data with prokaryotic system. This is what happened when I went to IIC. I gave this talk at molecular biophysics unit. They were very thrilled. One student said, why don't you see prokaryotic systems and see what happens in prokaryotic systems? And I saw, voila, same thing in prokaryotic system also. Same thing. Same ADP binding sites, same cavities, same cross access channels, same things. And very beautifully, this complex 4, there are 2 types of complex 4 in this system. One is when it is in anoxic conditions, when it grows low oxygen conditions, and one in high oxygen. In the high oxygen one, the ADP binding site is there. In the low oxygen one, it is not there. Very beautifully this theory explains thermogenesis. If you see a very simple thermodynamic concept, if proton pumping going from here to there is exergonic, coming across will be endergonic. Now, current theory says that heat production is by virtue of transmembrane potential dissipation. Okay? Transmembrane potential, when it dissipates, heat is formed. How? From here it is exergonic, while it coming back, how it can be? And for example, there is a transmembrane potential. How does it make ATP? You tell me. It's a magic. Just because some people believe. Most important, cyanide. Can I have your attention? Cyanide, this is beautiful. You will buy this. Cyanide is beautiful. You will buy this. Cyanide, Dr. Mukhopadhyay, see this. Cyanide is supposed to bind to complex 4 or all heme proteins. That is the current theory. Okay? Now, and therefore oxygen cannot bind, whether it is cytochrome oxidase or hemoglobin or all the heme enzymes. My theory says that this is the way cyanide acts as the inhibitor. It messes up the Ross dynamics, it makes water, and it doesn't allow the ATP formation. Okay? Now, you see, this is hardcore data. Anybody can sit half an hour, 1 hour, I can tell you what this data means. This is simple data. It's not done by me. It is done by people. The KD data, KM data, and the IC50 inhibition constants, the K-on data, very clearly say that the cyanide binding is a very slow process. Within a few seconds of you biting a cyanide capsule, any animal, any human being dies. You can live without oxygen for even 3-4 minutes. Many people. Why do you die so quickly? Because radical reactions are fast. When you take out ROS, which is the quintessential elixir of life, ATP is depleted by the complex 5, which is supposed to be the ATP synthesizer in the current theory. It is not. ATPase is ATPase. Here, very clearly, if you see a dosage calculation, as per the current theory, to bind to heme centers, you need grams of cyanide. Per my theory, you need only micromolar levels. Per my theory, you need grams of cyanide to kill. Grams per kg dose you need. Per my theory, you need only milligram per kg, which is what you see. If you see binding, carbon monoxide is a much stronger ligand than cyanide. Universally accepted fact. Most smokers have 10% carbon monoxide level in their blood. 1% cyanide is enough to knock you out, kill you. 40%, 50% is needed to take your consciousness away in carbon monoxide. What is heme binding? Nothing. It is not a theory at all.
No, but Murali, are we open to questions now? See, for instance, let me tell you here also, you are taking the entire body and you want every heme molecule to be blocked before you have death. You can knock off, for instance, the heart or the brain, you get dead.
Yeah.
See, the thing is that you have to actually look
I made that calculations. That book, that is already published. See,
I'm sure that your thing
that is there. See, this work is there in Bioxif. And very importantly, let me just say this last couple of more things and then we're done. This part is the most important aspect of the machine logic, the powering logic. This is spontaneously evolvable. Mine is like a nuclear reactor or a Earth kind of logic. It's just a fortunistic event. It is not a deterministic or a irreducibly complex event. Okay? It's like a nuclear reactor wherein the radicals go rather than the neutrons and all that. Here is free radicals. Okay? Now, per my theory, if a spontaneous nuclear reactor is something that my theory, stochastic theory, comes closest to. Now, in Oklo, on Earth, several billions of years ago, this was a reality. This kind of a nuclear reactor worked for hundreds and thousands of years. So spontaneously, my reaction logic, which is based in stochastics, can originate and can function. And it explains the formation. This is the last slide of my evidence. It explains the formation of transmembrane potential. The negatively charged ROS within the mitochondria are the reason for the transmembrane potential, not proton pumping. Then, why does cytochrome C leaching lead to apoptosis? Evolution said when it is broken, ROS gets out. So, cardiolipin, negatively charged, to keep superoxide within. High proton effects. Protons affect so many equilibriums, so many kinetics. That's why proton was showing all that evidence. I have explained every single standing evidence for chemiosmosis theory in my paper. So, why did evolution choose for lipid membranes and not for, say, glycoprotein, all that? Cohn's 1950s experiment, Mildred Cohn did a beautiful experiment. She labeled oxygen 18 and showed that phosphate, ATP is phosphate at multiple O atoms. Multiple O atoms can only get in through the radical reactions. Boom, oh. That is the fast one. This rotating and all that cannot explain that. Vitamin A, it's a it's a mitochondrial toxicant. It's a raw scavenger. Dinitrophenol is also an interfacial, all that. Ionophores, all this. Rotinone, I've shown. Rotinone binds at complex 1 at the same site where ADP binds. So, cationic lipids, why? Then it agrees with Occam's razor and the theory of evolution also. So, yeah, so basically oxygen is the life giver and the life taker. Thank you. And yeah, so I project that this is involved in cellular homeostasis, threshold physiology, signal transduction, neuronal potential relay, cybernetics, redox diseases, evolution, diversity, epigenesis, biosphere interactions. So yeah, a new theory does not triumph by convincing its opponents and making them see the light, but rather because its opponents eventually die and a new generation familiarizes with it. This is what Max Planck said. He provided evidence to this theory by opposing Feynman. You know? So, yeah. Yeah. Feynman, I'm very confident of what I said. Please, he opposed Feynman's, he and both Einstein opposed quantum electrodynamics. Both of them. So, what happens is when people go on a particular path for a long time, they fail to see there are alternate explanations.
Well, I think the philosophy of attacking the establishment is well known in JNU, but we also know the success comes not from just...
Well, but you did not exhibit your...
I am telling you the way that you have to do it is that in the scientific base you have to actually present what is the state.
Nothing is presented.
No, this is a good slide to...
Yeah,
in fact, this is the only data that we can do.
yeah.
Now see, if you had data like this that presented...
Andrew.
I mean,
Yeah.
but no, the problem is...
Please go ahead.
Okay, so
Yeah.
the question. Now, yeah, if you want questions, we can have it, but I think since the audience...
Anybody who is interested in questions, please.
Look,
Okay,
for
why
instance...
when people think that ROS is very not good for the cell, when you are saying they produce more, you can censor the ATP.
That is a paradigm shift that I am saying. Now, oxygen is a diradical. Oxygen is a diradical. Why did life focus on this? Because lipids are electron rich. By having that lipid interface there, covering there, now you have an electron rich grounding. Now you have something transiently produced ROS here. Now this ROS will go towards the lipid. And by this, within this, you are harnessing that ROS. ROS are immense, they're fast, they're highly efficient.
So what is the role, I mean, like ATP?
Oh yeah, sorry, that's a very good question. Let me come to it.
What is the reaction that shows that?
This is the reaction. Now this, oxygen goes from oxygen to water. In the meanwhile, these two radicals are produced. Now these radicals can attack phosphate and ADP. It's not rocket science.
No, can I come back to not rocket science because it's our textbook stuff on, for instance, cytochrome P450 and xenobiotic distribution. I know that mutations in cytochrome P450 that we get from genome-wide association studies can change the effect of the cytochrome P50 on xenobiotic breakdown.
Sure, it can.
How? In philosophy,
Sure.
how?
Oh, no.
Mine is that there is a concept of substrate specificity. Let me finish what I'm saying.
Yeah, please.
So what we have is that we model the vibrations, so to speak. We call them correlated motions, and we correlate this to induced fit. And therefore, we can say that certain substrates, you don't have to have specificity at the level of standard enzymology, but when you have substrate divergence like this, you still have a loss of some substrates and some substrates being bound because of this. But it's still the classical substrate specificity that comes from binding to a protein. So how is this different? I mean, how can you explain this with yours? And in yours, you simply can focus ROS much like we can say pH is responsible.
This is what I was trying to explain. The point is, I'm not saying there is no binding. Here also there is binding. In complex 4, complex 3, complex 2, there is binding. But it is not here. There is no induced fit, nothing like that. Here it can bind anywhere. So it is not at the heme active site. So what happens is, now you have a random, there are P450s, there are 40, 50 P450s. Now they have different topology, okay? All their surfaces are like binding sites. All their surfaces are binding sites. Now you have a potentially n number of binding sites.
Okay. All right.
Got it? Yeah, that's it.
But you said something I don't know, understand.
Yeah, please.
You said water is pumped out, is it not?
That is the current theory. I'm saying it's not. There are no protons to pump out. That's my argument. The current theory is protons are pumped out.
I'm sorry, I have to leave. I'll only make one comment on Mali.
Dr. Govindji, thank you for your...
No, I only want to make one comment. I think you're killing yourself.
Thank you, sir.
Because if he would...
Let's see.
No, let me say that.
Yeah.
If he would present his theory to us, step by step, and explain it, then we will understand it. And that will be to your benefit and the benefit of the world. I know you are very brilliant and you have many new ideas, but you have decided to work the system so that the system works against you. And if this is what you want, you are welcome. I mean, I think work like this should be published in Nature, should be published in the very top journals, but the reason it's not published is not because the work is bad, because I cannot judge the work, but it is you, because you are not, you gave this whole seminar, instead of explaining your theory, how it works, what it means, what it fits, where's the experiment, you're going round and round, and every sentence you're saying, now you will understand, or you would know this. So I think your method of speaking is your enemy. And unless you do this, I would like you to get a Nobel Prize to believe me. But with this method, you are killing it instantly. Because you do not understand that the debunking Mitchell theory. I mean, this is the most useless word that you have ever used. No, do not. No, I don't. Yes, you aren't being recorded. That's wonderful for you.
He's the source of my inspiration.
No, it does not matter who is the source. You are the one going around the world and talking, and you are the one.
Word, sir.
Yes, you are, through your papers.
Yeah.
All right. So I think
science does not accept authorities like that, Dr.
No, it has nothing. It is your way of doing. There was something, Kalidas or something, I forget, I'm not very well versed, that he sat on the tree trunk and cut himself so he falls. So I don't want you to fall. I want you to be successful. But you please listen to reason, way of presenting, the way of writing. If you constantly attack, you are attacking yourself by doing that.
But actually, to give him, but Murali, I mean, this is something that now you should remove from your presentations to a scientific audience. But Professor Govindji, for the past 4 years, the question is, where have you published this? You know, so now that he's got it published, I
yeah,
can
but this is not the forum to give a seminar to say where of course everybody knows where you are.
No, but until 4 years back, this was not.
So Govindji, why did I put that? Because you keep on saying that this work It's controversial. The last mail that
Of
you
course
sent
it
was-
is controversial.
Why is it
It is
controversial?
controversial because of you.
Why?
I'm telling you. Because you don't know how to present it. You don't know how to write it. You don't know how to do it. You have to use simple, I even read your abstract. 10 words are there. So you want those people who know top English, their bombastic English, they'll understand. Not a simple-minded things so that the common man, publish it in Nature. And your work is that it should be published there. But you are not working in that end, you are working opposite. You are killing yourself by not listening to see how you can present your talks, how you can write your papers, so that people will understand your theory. I'm sorry, as I said, take my PhD, take my professorship away, because I mean well.
Say that.
No, you didn't say that. I'm saying that. I mean well for you, and I believe in you. That's why I wanted you to be here. But you disappointed me by not explaining your theory from the step one. I've never ever said that in my life to anyone.
I think it's a matter of difference. In India, we don't question. I'm glad you're coming here. You've got the best of both worlds. You sort of question the way that.
As I said, I've taught for 40 years, and I've listened to speeches after speeches, and talks after talks since 1956.
But
to Rudy Marcus, who came to Urbana.
Professor Govind, what is the thing? It hasn't come to the question where we've got the concepts to argue. We are attacking the
I know, we are attacking the man because he did not bother to explain the concept.
But doesn't matter.
Dr. Govindji, I have given you the papers.
No, don't, that's another thing. That is again very wrong for you to say, I've given the paper, God damn it, you read every word and you should understand it. No, you should be able to write in a way that people understand.
A man can take...
No, don't explain, because this is a problem, and it continues to be a problem. So unless you learn that you have a brilliant idea, and you have to learn to sit down, to write it in a way that people will understand step by step.
So see, Murali, the thing is, it's gone into a tangent which you
No,
have to take.
the tangent I know.
No, the tangent you should take
I have
more
presented
seriously.
it,
I've known you
it's
for
so
25 years. So the thing is that you should not be aggressive about attacking.
What?
You are aggressive, but mind you that your words, even when you're talking to